Okay, let's have a look at the relationship between pressure and volume in gases, which is otherwise known as Boyles Law. And for this relationship, we assume that our temperature and the mass or the amount of gas that's present is held constant. So we can set up a simple apparatus to measure change in pressure and change in temperature. So on the board here we have some sort of piston which has a cylinder with something with a measuring scale, and we have our piston inside attached to something that we can change a mass on top. And if we look at the relationship between pressure and mass, remember our pressure is equal to force over our area, or our surface area, and force is equal to mass times acceleration due to gravity. If we know our acceleration due to gravity, we can measure our mass, which means we can measure our force. We can measure the force that we can measure the area that this force is being applied to, which then gives us a measure of our pressure. And if we change the mass on our piston, what we find is that the volume within our cylinder, the volume of gas within our cylinder, changes as well. So let's explore that relationship a bit more deeply. As we increase mass, we therefore increase our pressure, and we find that our volume decreases. So I've just given us some simple units here of 1 something, 2 something, and 3 somethings. And as we can see, if we increase from 2 to 3, the volume decreases. So we can also graph this out. And I've just got a set of results here that are a generic set of results. So we've measured our pressure in atmospheres. We've measured our volume in cubic centimetres. So in our first example, we've got 0.95 atmospheres, something close to 1 atmosphere. If we increase that all the way through, we find that with our volume, we actually go down. So for approximately 1 atmosphere, we've got 1.5 cubic centimetres. If we increase the pressure to 1.14, our volume decreases. And if we keep increasing it up, we see that there's a trend for that volume to decrease. Now, there are a few observations that we can make from this set of data. First of all, if we multiply pressure by volume, we find that we get a pretty constant value. So that tells us the relationship between the pressure and the volume for a closed system will always, or if we multiply them together, we'll get a constant value. We can also graph these results out. So on the left-hand side, we have a relationship between pressure and volume. And if we increase the volume, we decrease the pressure. Or if we increase the pressure, we decrease the volume. Now this sets up an inverse relationship. And if we graph this in a slightly different form, it makes more sense. So if we put it as pressure versus 1 over volume, we actually find that we have a linear relationship. So what can we say with these 3 pieces of evidence? First of all, we can say pressure is proportional to 1 over volume. That's from our linear relationship there, which then we can further quantify by saying pressure times volume is always equal to a constant. And this gives us a very useful relationship because we can further expand on that particular relationship to give us something that is very worthwhile. And we commonly see Boyle's law in the form of P1V1, so our initial set of conditions, where we've got the first pressure times the first volume, will always be equal to, because it's equal to this constant, the second pressure times the second volume. So how can we apply this to calculations? Let's take an example. Let's say that we're given an initial pressure of 765 millimetres of mercury as our initial pressure, and in a closed system, that particular gas occupies a volume of 1.78 litres. Now once again, we're not concerned with changing, or we don't have a change in temperature, and we don't have a change in mass or amount of gas in there, so we can look at this relationship. After an experiment was completed, it was found that the volume was 1.25 litres. In other words, we've reduced that volume. So what will happen to the resulting pressure if we apply this reduction in volume? Well, if we look diagrammatically, we go from 1.78 litres to 1.25 litres. Something should happen, or something should change in the pressure as a result of that change in circumstance. So the first thing we need to do is write down our equation. P1V1 is equal to P2V2. The next thing we need to do is isolate for our term that's our unknown. And in this case, we're looking for P2. So we need to divide both sides by V2. And that will isolate our P2 on one side of the equation. So in this case, we've got P2 is equal to P1V1 divided by V2. And then if we apply our numbers through this equation, we get 765 millimetres of mercury for our P1, we get 1.78 litres for our V1, and we divide that by 1.25 litres for our V2. And our litres are common top and bottom, so we can cross those out. So our final unit should be millimetres of mercury, and if we work through the calculation, we should get 1,090 millimetres of mercury, or 1.09 by 10 to the third millimetres of mercury. Now, does that number make sense? Well, let's look back at what we did. We decreased the volume, therefore our pressure should increase. And is that what our number is telling us? We've gone from 765 millimetres of mercury to 1,090. So yes, we expect this to happen. So our answer, assuming our calculation is correct according to our formula.